Okay guys, what I want to do is we're going to discuss the concept, the inverse of a function, and I want to do it by going through the investigation. Okay, oh wait. I want to go through the investigation that we did in the beginning of the year, well some of you only recently. And with the investigation, we discover what an inverse actually is. Okay, so let's start by just answering the questions based in here. Give me a number.
-1.
-1. Gulani?
I see
2. Kudwa? 4. Cassandra? Paulina? 6. And Cassandra? -3. So notice now this is called a function machine. And what we do in a function machine is we take the number that is put in, and then we substitute that number into the function. Guys, I just want to check something quickly. Okay, so all we're going to do is take this -1 and substitute it in there. So we've got 2 times -1 plus 4. 2 times -1 is -2. Plus, or let's actually say, Masande, what would be the first answer for fx? So fx means I take this x value and I substitute it into the x here, which is 2x. What will your value simplify to?
-2.
No? Not your calculator, come now. So each of you take your number and you're going to give me your answer.
It's 2.
Positive 2. To Kudzwa, if I put in 2 in here, Kulani? 8. Okay, so I put the 8 in here and add the 2 in there, and I get 2 times 2 is 4 plus 4. 8. To Kudzwa? 12. Is that Cassandra?
16.
Oh, 16 first is and -2. Is it -2? Yes. Okay, great. Now that would be the first part of the function machine. Now what I want you to notice is that there's a next part. In the next part we have g of x, and g of x is asking is a different formula or different function, and this time what's going into g of x is the fx values. So in other words, now I must take a 2 and I must put the 2 in here, not the original value but the value of 2. What answer do we get if we do that, Ms. Sander?
-3.
No, look carefully. So it's a half times 2 gives you what?
1.
1 minus 2?
Or it's -1.
-1. Excellent. Kulani, what do you get?
Take the 8 times a half, which is 4. 4 minus 2 is 2.
It's 2. What do you get, Tekudzwa? 12?
Yeah, so I get 12 minus 4.
No, 12 times a half is?
That's 6.
Minus 2? 4, positive 4. Okay. Paulina?
It's a half of 16 is 8 minus 2 is 6.
6, excellent. And then Cassandra?
It's a 3.
It's?
3.
You sure?
It's a
3. Excellent. What do you guys know? So that was the first part. Okay, now they say, describe the process and outcome of this number machine as accurately as possible, as well as what you are noticing. You use words like input and output to refer to the numbers that are being fed into the machine and produced out on the other side. Also make a clear distinction between the two parts of the system. So here's the first part and there's the second part. So who can tell me, what do you notice?
It's equal to what you had at the start.
Okay, yes.
It's equal to the output.
The output is equal to the input, but first we have values that's being put in and producing an output called f of x. If we then use that output and put it into g of x, we have a new output, and that output is equal to the original input. You see that? Okay. Now, what The next question is asking, what should the function notation be at the question mark? So here at this question mark, notice this is f of x because we took the x value and we substituted it into f. What should the value be here? It can't be g of x because we didn't substitute x. This is x. If we say this is g of x, then it means we substituted x in there. So this is the function g of x, but we didn't substitute x. What did we substitute? We substituted f of x. So what it should be is g with f of x in. Do you understand? So in the place of the x's, we substituted the fx's. Does that make sense? Okay, good. Now, what do we notice about this expression? This expression is equal to the x. And that's what it says. Which of the following is a mathematical description of what happens? Is it true that if we put g of x into f, that we get g of x again? Is it true that if we put x in g, we get x?
Yeah.
Yes, this one is true. Is it true that g of x is equal to f of x? No. Is it true that g, if I put f into g, that I get f? If I put f into g, do I get f? No. If I put f into g, I get the original x. So in other words, if it was this bottom one, it would have meant if I put this values into that, then I get this values again. That's not what we see. We see if we put this values in there, we get the original values. Does that make sense? Anyone have questions at this point? No. Okay. So in the so this is the answer. In the question, you then pressed next. You went to the next question. You couldn't go back. And in the next question, we explain this. We say that the function g is the inverse of function f if it reverses the function f. Isn't that what happens here? F causes the x values to produce this. G causes this values to be reversed back to the original values. Do you see? And that's what the inverse does. Is it takes the input and I get an output. If I take that output and I put it into my inverse function, I'll get my original input. Is that making sense?
Yes,
A bit. I'll give you an example of an inverse function. I will ask you, who's your daddy? Petra, what's your answer? You can say his real name, you don't have to.
David.
David.
Yeah.
Okay. Now what would be the inverse question?
Who's your daughter?
Who's your child? Yes. Do you understand what I mean? Okay. So in other words, with my question, who's your daddy? I'll get the answer to the father. And I'll have to ask the question to Petra, to the child. The inverse function is the opposite question, is who's your child? And I don't ask the child who's your child. I ask the father. In other words, I take her answer and I ask that answer the question. Does that make sense? That's what we mean by the function g is called the inverse. So if I say, who's your daddy, is who's your mommy the inverse of that? No, it's a different question. It doesn't, the answer she give, I can't put that answer in this question and get the original answer. Does that make sense? Okay, so maybe it's just a little bit up in the air. We'll look at the math application just now. Look here. If this is f of x, and that is g of x, prove that g of x is the inverse. So notice here, they say, in other words, if f is evaluated with an input, in other words, we put an x value into f, the output is f of x. Okay, it's now the answer that I get when I put it in. And if g is then evaluated with this f of x, in other words, I take this answer that I got and I now put it into g, and the output is again x, in other words, what I originally put into f, then g is called the inverse. Now how could we prove that? In other words, it's what we saw in the previous one. In other words, if I take my f of x and I take that out, that answer that I get from f of x, and I put it into g of x, and I get my original answer that I put into x, my original value I put into f. Okay, so now we must use this to prove that these two are inverses from each other. And so they give us a clue here. We must take g, and in the place of x, I must put f of x. So let me do that for you. So I've got 4 and 5 and a quarter. So they tell me that f of x is equal to 4x plus 5, and they say g of x is equal to a quarter x minus 5 over 4, and they ask me to show that these two are inverses of each other. So if I take g and I put fx into g, what do I get? Okay, so we take g, here's the function g, but everywhere where I see x, what must I substitute? 4x plus 5. So where there's an x, I'll now put a bracket, and I'll put everything that f of x is 4x plus 5. And then that was just, all I did so far was replace the x. There's still the negative 5 over 4. Does anyone have a question at this point? Do you understand what I just did? Okay? And now all I'm going to do is simplify. I multiply the quarter in here. So quarter times 4 is what?
1.
So 1x. So 1x. A quarter times 5 is 5 over 4. Because it's 5 over 1. So 1 times 5 and 4 times 1. Minus 5 over 4 is still there on the outside. So here you see this and this cancels. And what am I left with? Just x. Do you see? When I put f of x into g of x, it simplifies to the original value. So let me give an example now. Okay, let's for example take the value, let's just make it easy for ourselves. Let's say x is equal to 1. If I take x is equal to 1, then f of x is equal to 4 times 1 plus 5, that's 9. Now if I take 9 and I put 9 into g of x, so now I'm putting g and f of 1. Do you notice what I did there? Sorry, this is not f of x, that's f of 1. Now I take f of 1 and I put it into g of x. Now f of 1 is 9. So I must put a 9 in here. That gives me 1 over 4 times 9 minus 5 over 4. 1 over 4 times 9 is 9 over 4 minus 5 over 4 is what? 9 over 4 minus 5 over 4? Someone answer me immediately.
It's 1.
It's 1, thank you. It's 4 over 4. 9 minus 5 is 4. 4 divided by 4 is 1. You with me? If I see you use a calculator for this, I'm going to eat your calculator. Okay, let's go to the next question. So the next one, so that's what I had to do here, is I had to substitute the x value, and then here I should have gotten an x as an answer. Okay, when I simplified. Okay, draw both functions on the Cartesian plane. Who can draw a straight line? Why aren't all of your hands up? Thank you, Kulani. Kulani, how would you go about drawing this first one?
The first one, like first I drew, you know that little thing?
No.
Like
A little box.
Yeah.
Are you using a table method?
Yeah.
Okay, let's make it easier. Let's just take any two x values. You don't need a table, guys, to draw a straight line. Use 0, good. So if x is 0, y is?
It's f times 0, which is 0 plus 5. It's 5.
It's 5. So my first point is going to be at
0 and 5.
0 and 5. Now choose just one other point. To draw a straight line, I need 2 points. That's it. And I connect them with a line. Where can I get the second point? Petra?
Where's the first point, sir?
The first point is when I put a 0 in here for x. then I get a 5 for y. So here's my first point.
Okay. Then let's put a 2 for x.
Okay, so a 2 is fine. The only problem is if there's a 2 there, I get 8 plus 5 is 13. And my graph doesn't go that high, so let's rather go for negative numbers. Negative 1 is a good one. So negative 4 plus 5 is?
Is 1.
1. So in other words, I've got 2 points. I've got 0 and 5, and negative 1 and 1. So there's my first line. Let's draw the next one. Okay, to Kutzwa, your turn.
You substitute 0 there on the x, right?
And then you get?
You get
minus 5 over 4. It's not a lovely one to draw, but that's okay. So we get minus 5 over 4, and then another one, Cassandra?
1.
If I put a 1 on here, that's a very nice one. If I put a 1 in here, I get a quarter minus 5 over 4. So it's 1 minus 5 is negative 4, and negative 4 gives me negative 4 over 4 gives me negative 1. So I've got 0 gives me negative 5 over 4. How much is negative 5 over 4?
1.25.
It's negative 1.25. So it's here and about there. And then when we put in a 1, we got negative 1. Good. Now you'll notice with these two graphs, you might not notice it easily, but you'll notice that if I draw, it's not coming out nicely now. I must lift this one up a little bit. Okay, if I draw the line y is equal to x, the line y is equal to x means when x is 1, y is 1. When x is 2, y is 2. When x is 3, do you see? This is the line y is equal to x. Then these two lines must cut in that same line. You notice there? Okay. That means it's they're the reflection of each other in this line. So you'll see this one, for example, has the point 1 and negative 1. This one has it turned around, negative 1 and 1. This one has the line, I should actually fix it a little bit. There we go. This one has the point 0 and 5. 5 and 0. This one has it turned around, 0 and 5. Do you see? They have their x and y values turned around, which we weren't supposed to draw that one, so I'll leave it out. Okay, now we must do this one. Okay, let's go and prove that these two are each other's inverses. How about you guys try that one? Try showing the same I did now with the straight line. Show for me that if f is this, so in other words I'm doing the same that I did here. You have an f value and you f function and g function. You substitute f into g, and then you must simplify to get x. See if you guys can do it for these two functions. So it basically comes down to this, that, and I'm not going to test it again, that if we have, what was gx? Was that the 2x squared? Fx, it doesn't matter guys, let me actually do it the other way around and show you it also works the other way around. You all did it now by substituting this x with gx. Let me show you if we take f and we substitute g of x in there. Will it still work? Well, let me show you. Here's f. Oh no, wait. It was the other way around. Okay, so let me now show you then. Will it work if I just swap these two around? Okay, so in other words, if I replace the x here with the f of x, you see, then I'll take the square. Sorry, that should be a half. Yeah, sorry. So I have the square root of a half x. Okay, so what did I do? I replaced the x. The x had a square. So when I replace the x with my brackets, I must remember to have a square. So now on the inside, I'm going to, what does the square do? It eliminates the square root. Because square root means to the power of a half. If I have x or anything, let's do that. If I have anything to the power of a half, and I square it, what do I do if I have a power with a power? What do I do with the exponent? multiply. So a half times 2 is 1. So you see, that's why a square root of a squared, why they cancel. The square root has an exponent of a half, and then when I multiply the exponents I get 1, so there's no more half exponent. So this one, that's what will happen in here. The square root will cancel, so I'll just be left with a half x, and then when I multiply it I'll just be left with x. You see that? Everyone okay with that? Let's go and draw it now. Now they ask me, plot 5 points for each function and draw in the correct graph for each function. So you can see here my values go quite high, up to 50. So I'm going to use square numbers. So I'm going to use 1. 1 squared is 1. Oh, let's start with 0. No, let's start with 1. 1 squared is 1. Actually, let me start with 0. Why not? 0, if I get a 0 for x, 0 squared is 0, times 2 is 0, so that's just 0, 0. Next one. 1 squared is 1, times 2 is 2. So when x is 1, that's here, y is 2. The next one I'm going to use is 2. 2 squared is 4, and then 4 squared is 4 times 2 is 8. So 2 gives me 8. The next one is 3. 3 squared is 9 times 2, 18. So when x is 3, that's halfway here, I go up to 18, which is there. The next one is 4. 4 squared is 16 times 2, 32. And then 5 is 25, and that's why this one goes up to 50. We'll go up to there. Okay, and now guys, I'm just going to use the opposite values. Okay, because I'm doing square roots, so I want nice values. So let's take values that I can take the square root of. What value can we take the square root of? Square root of what do you know?
1.
The square root of 1. So what must x be so that under the square root I can get a 1? 2. So if x is 2, g would be 1, because it would be a half times 2, which is 1. The square root of 1 is 1. So if x is 2, y is 1. Give me another value that you can take the square root of. Don't tell me 1 is the only one you know. What's the square root of 3? No, that's the square of 3. Square root is what must I multiply to get 3? 9. 9 will work, okay. So what must x be so that underneath the square root I get 9? So I can't put 9 in here because 9 divided by 2 is 4.5. What's the square root of 4.5?
Put 18.
18. If I put x as 18, 18 divided by 2 would be 9. Oh, come on, K. 18 divided by 2 is 9. So if x is 18, the square root of 9 will be 3. So if x is 18, y would be 3. Okay, next one. 16. What must I put for x so that I have 16 under the square root? 32, because I take the half of that. So if x is 32, I would have 16 under the square root, and that would give me 4. Okay, something seems weird here. Oh, I just didn't plot 4. Okay, I'm going to put that one in just because we're going to run out of numbers. If I want underneath the square root to be 4, what must I put for x? 8. Good. So I've put an 8 in here, then I get underneath the square root of 4. So if x is 8, y would be 2, because I would get 4 under the square root and the square root of 4. Is everyone okay? Are you getting what I'm doing? Are you a bit confused, Cassandra? Okay, so if x is 8, a half times 8 is 4. The square root of 4 is 2. So when x is 8, y is 2. Okay? And then the last one, what can be another square root we can calculate? We've done 9. 25. What must x be so that I can take half of that to be 25? 50. So if x is 50, then inside the square root I'll have 25, and when I do the square root I'll have 5. So when x is 50, y would be 5. Now again, notice it's exactly the same. So there's the graph. If I drew it, it would look like this. Here's this one, and here is that one. Okay, so there's the two graphs, and notice where the one I have 2 and this one is 2 and 1, that one is 1 and 2. This one is 2 and 8, that one is x is 8, y is 2. You see, x's and y's are swapped around. That's exactly what happens with the first. So that's the next question. Describe the relationship of the graphs. Now once again, notice if I draw in the line y is equal to x, then they're a reflection. It's as if this line is a mirror. This line is not correct. Let me draw it in here. This line is a mirror. Okay? And whatever happens on this side happens in the opposite on that one, like we're seeing each other in a mirror there. You see that? Okay, so with that in mind, describe the relationship of the graph of f and g. G is the reflection of f in the line y is equal to x. Okay, so this isn't called an investigation because we discover what the answer is. We don't know what the answer is. We're discovering what inverses are. Now that's why in question 3 we give you the answer, the graph of the inverse. The graph of the inverse of a function is the reflection of the function in the line y is equal to x. Okay, so now we tell you what it is. So reflect the two given points in the line y is equal to x. Now what a reflection is, it means I would take this, the distance from here to there must be the same as the distance from there. For example, if you stand in front of a mirror and you stand right up front in the mirror and you step one step backwards, what has your image in the mirror done?
Small.
Yes, but it also took one step backwards. Okay, for you it looks smaller, but if you were on the other side it wouldn't be smaller, is it?
Yeah.
If there was another side, I find mirrors very freaky. Okay, point being is the distance that you are from the mirror is the same distance that your reflection is from that mirror. Does that make sense? If you were able to jump into the other side, you'd measure the distance. So the distance from here to there must be the same as the distance from here to here, and we can see he goes kind of like 1, 2, 3 steps sideways and 1, 2, 3 steps down. So 1, 2, 3 steps sideways, 1, 2, 3 steps down. That looks like a reflection. Okay, this one goes 1 step sideways and then he's already there. And this one will have to go 1 step down. Can you see the reflection?
So basically just swap the
And that's exactly what we see again. That's the next question. Okay, well, here at the bottom it says, if the coordinates x, y were reflected in the line yx, what would the new coordinates be?
Yx.
It would be y, comma, x. Okay, so if we reflect in the line y is equal to x, the new coordinates would be, or x, comma, y, the new coordinates would be just those two values swapped around. Okay, so let's look at the question that I skipped. Match each of the graphs on the left with the inverse graph on the right. Okay, so notice this one. If I were to draw the line y is equal to x in here, and I were to reflect it, will it look different?
It would kind of look the same, just like.
It would look exactly the same. This graph, if I draw a line here if I connect that line is already a symmetry axis. It's already cutting it perfectly into two sides that will fall on top of each other. Now, if I reflect something in a symmetry line, it will look exactly the same. In other words, that's exactly by saying what will happen if you were to stand in your reflection side. Will it look the same? Yes, it will look the same. Okay? So this one, the inverse of this graph will still look exactly like this graph. So let's find it. Is it that one?
Looks like it. Will you please go up again?
Can you see it's not the same? Yeah, this one is in the third and the second and the fourth quadrant. That one is in the first and the second, third quadrant. There we go. So this one must be E. Okay, the second one. Now notice. So notice this graph. What is he getting close to? He's getting close to the x-axis, isn't it? Now we say the x and the y values swap around. So the inverse will go close to what? The y-axis. But now there's two parts to the y-axis. Will it go at the top closer or at the bottom closer? At the bottom closer. Why? Because we're trying to reflect in this line. If this one is going closer to the negative x values, the inverse will go closer to the negative y value. So this graph must look like this. Does it make sense? Actually, no. This graph will look like that, because now look at this. This one, when he comes to the positive x values, he goes to the negative y values. So here, if I go to the positive y values, I must be going to the negative x values. Let's see if I can actually just copy this picture there. Okay, so notice here, I've drawn it in there. So let's draw in our y is equal to x line. See if that will help us. So if I draw it in more or less, you can't see that, can you? You see that? Should I use a darker color? Okay, so there's my y is equal to x, more or less. Okay, and now I must try and draw in the reflection. So let's look at this part. If I were to draw in this little leg here, I will go from here like that. Do you see? And if I draw this in here, if I reflected this one, it will look like that. Can you see it? Can you see how that's the reflection? Guys, this thing you have to practice. So go and look at different shapes and reflect it in the y is equal to x line, so that you can practice in what the reflection, and they will definitely ask something like this. Definitely. Okay. The way I do it, I don't actually go and draw it in. I go and look, okay, this one is approaching x negative, so the inverse must approach the y negative. This one is going away from the y positive, so the inverse, sorry, this one is going away from the x positive, so this one must go away from the y positive. And so then I see what is it coming close to, what is it going away from, and that gives you my shape. And then I draw it in, and I mean this one is also approaching the x and going away from the y positive. So there's two options. But this one is clearly not the reflection of that one, because the reflection must meet in that point. Does that make sense? So there where the y is equal to x cuts, my original, my inverse must cut in that same point. It's like when you touch a mirror, the other side is touching the mirror at the same place. If it doesn't, it's very freaky mirror. Okay. Okay, so let's get back to that one. So this one's inverse. Shout if you see it. Yes,
Doesn't look full.
it doesn't look full, right? But it's not. It's because the graphs are too small. The computer can't generate the small values there. But you're right, it should be that one, I. Okay. And then the last one, this straight line. Let's see if you guys can see which one. I didn't, you're right. Okay. See if you can see that one. How will you describe this one?
I can see that it runs through the negative, like
There's a point of negative x and
Yes.
y.
Okay, good. So at negative x and positive y. So the inverse what must be what?
Positive. Negative y and positive x.
Negative y and positive x. So negative y and positive x. Okay, so let's see if we can find a negative y and positive x. That one? No.
J.
Yeah.
That's it, huh?
Yeah.
Negative y, positive x. Let's just see if there's not another one. No. So that would be J. You get it?
Get it, got it.
J. Okay, let's go on. And so the next question would just ask you what would the new coordinates be. Okay, so that now gives us a way of how, so far we haven't seen how can I find the inverse function. We've just been able to test whether two functions were inverses by taking the one function, pushing it into the other function and simplifying and see if I can get x. Okay. So now here they tell us that this is how we will get the other function. The transformation rule for a reflection in the line y is equal to x is given by this. In other words, if I take something and I reflect it in the line y is equal to x, this is exactly what will happen. Every coordinate will swap. X's and y will swap. In other words, to find the inverse of a function, we can follow these steps. We replace x and y, and we replace each x with y and each y with x. That's exactly what we're doing here. And then we just solve for y. We get y on its own. So let's look at that one, for example. Y is equal to ax squared, ax plus b. So if I have y is equal to ax plus b, step 1, swap x and y. X is equal to ay plus b. And step 2, get y on its own. Solve for y. So I've got ay is equal to x minus b. And so y is equal, divide everything with an a. So there's a 1 there, so it would be 1 over a x minus b over a. Now let's quickly go, if you...
Can I ask a question?
Yes, of course.
You see the x, we put it on the other side, so it's x minus b, right? And then we have to divide everything by an a. Won't it be like x over a?
So in other words, okay, it should be x minus ax minus b. No, sorry, x minus b. It should be y is equal to x minus b over a, like that. Because I divided here
Yes, sir.
both sides with the a, like that. Are you okay with that step?
Would that be wrong?
It wouldn't be wrong. I wrote it like this so I can show you something, but let me show you then what will happen here. Is now I distribute. There's two terms, so I take the denominator and give it to each one. So this one becomes x over a minus b over a. Okay. Now this one here is one term. There's one term in the top. If a is something, let's say there was something in front. Let's say it was 8x over 2. What's this answer?
It's 4x.
4x. Do you see the denominator simply, if there's one term and that denominator is a number, like we're assuming a is a number here, then it's only dividing the number that's in front. The number that's in front here is a 1. So this is the same as just saying 1 over ax minus b over a. Do you understand what I did? Okay, so I just wrote it like this because I want to go back to, so notice what it did. The original one had an a and a b in. The inverse now have 1 over a as the gradient and negative b also over a. In other words, so look at the original one we had when these two were inverses.
So why don't you put the b, why don't you say 1 over a times b like the way you deal with the x. Do you get what I'm saying?
Why didn't I make 1 over a x over a?
No, like 1 over ax minus 1 over a.
Because b is also a value. B itself is a number, like, because this is for, look here, for example, my a is a 4 and my b is a 5. X didn't have a value, so that is why let's say b had a y there, just as an example. Then I would make it I would have made it, if it was x minus by over a, I would have made it 1 over ax minus b over a y, because b is also a value. That's the value that I'm going to divide, but there's just not a y there. Do you understand what I mean? So it is actually just a 5. So no, let me actually do the whole thing, then you'll see what happens. So I've got y is equal to 4x plus 5. First step, swap them around. So I get x is equal to 4y plus 5. So I've got x minus 5 is equal to 4y. And here comes the dividing everything with a 4. So I get y is equal to, now there's a 1 in front there. So 1 over 4x minus 5 over 4. Is that blue? Oh man. Okay. Can you see that? Okay. Do you get what I just did? I was now able to find the function. Now, if we substitute this function into that original x, the whole thing, it would be exactly what I did here. The whole thing will simplify to x. So this is the method of finding the inverse. You get it? So it's not always that easy. Let's look at this one, for example. Okay, y is equal to ax squared. Now this one is a very important example. This is typically the ones you get in the exam. Y is equal to ax squared. Step 1, swap x and y around, so we get x is equal to ay squared. And now I must solve for y. So I get y is equal to, or y squared is equal to x divided by a. You with me? But I must get y on its own. So I must get rid of the square root. I get rid of a square of the square. So I get rid of a square by taking a square root on both sides. But when I take a square root on both sides, it must be a plus minus. Okay, so that's what we find. We get two answers. We get a plus and a minus, a square root of 1 over ax. Okay, do you see what I'm doing again there with that 1 over a? Don't let that confuse you. Okay, but there's a plus minus. Now I want to show you guys just something important here when it comes to the graph. The first one's graph looks like this. The original, this one. The original one looks like that. Who knows what it looks like? What is that? What graph is this? Oi, no way. It's not an exponential.
Isn't that a straight line?
No,
Okay, we're down to
I'm just guessing.
yes, the same. Yeah, the same. Everyone's guessing. You've got two guesses left: hyperbola or parabola.
Parabola. No, hyperbola.
It's a parabola.
It's a parabola, thank you. So this is what a parabola looks like. Guys, that's terrible. That's really very sucky. That's what a parabola looks like. Okay? Now the reflection of the parabola, remember we said the graph will reflect in here. So we want to know, what does this graph look like? Isn't it? Aren't you curious, what does a root graph look like? A root graph will be the reflection in this line. Okay? So notice what will happen to this leg. It cuts here and there, so this one will look like that. Do you see this part? That is when x was positive. This is the leg where x is positive. Do you see that? All the x values are positive now. Then it reflects and gives us that part. Now notice this part, all the y values are positive. So y is equal to positive the square root of 1 over ax.
So all the x must be positive.
In here, all the x values must be positive because the original x values was positive. Now, in here, all the x values are negative. So all the x values are negative. You see? Now, when I reflect this one, it looks like it goes there.
All the y are negative.
Now all the y values are negative. So this would be the graph. Y is equal to, now the negative the square root of 1 over ax. And so here's the complete inverse. If this one was f of x, then this one would be called the inverse. I don't think I showed it anywhere, but that's the notation we use for the inverse. Has a -1. That's the notation for the inverse. And it's not something I talked about today, but I put on another video when I did it with the other class. I did with them just functions in general, so go and look at that video. We didn't look at the inverse. We're looking at the inverse with you, but when I did it with them, I told them that the inverse, a function, the definition of a function is that for every x value, we only have one y value. Now notice here, if I take any x value, how many y values do I have? One there and one there. Now we call it the vertical line test. If I take a vertical line and I can cut my graph more than once, it's not a function. So function isn't just something specific. A function is when I have, so for example, a circle is also not a function. This thing never. Like a circle is also not a function because when I draw a vertical line, I cut more than once. So circles aren't functions. A root function because of the plus minus. So if I wanted to look at the original graph, this graph, and I wanted his inverse to be a function, I had to restrict the domain. Restrict the domain. Now the domain is the x values that I will put in for x. That's what we call the domain. So if I wanted to restrict the domain, I would have had to say, well, I'm only going to look at x values that are bigger or equal to 0. Because if I look from here upwards, I would see that if I do this inverse, I would have only one value for every x. Or I could have said I will look at all the negative including 0. So in that case I would have been using this leg here. You get what I'm saying? And now when I take the inverse, so guys, are you sure you get what I'm saying? I took my whole graph in the beginning, but I can't take the inverse of the whole graph. Because if I take the inverse of the whole graph, I get two legs. I only want one. Because I want a vertical line to cut only one. So how can I only get one leg? By saying, okay, I'm only going to look at the positive x's or the negative x's. One of the two. I can't look at both at the same time because x's and y's swaps around. And if I have positive x's and I have negative x's, I will get the positive y's and the negative y's will give me two 2 answers for 1 x value. That won't be a function. Okay, it's simply not what we call a function. Okay, now how would you have known whether you should restrict the domain or whether you shouldn't restrict the domain? Let's go back to these graphs. If we look at these graphs, will the inverse be a function? What you do is, because you're swapping x and y around, the vertical line test will tell me if this graph is a function. Is this graph a function?
Yes.
If I draw a vertical line, it will always cut only once. Okay, so this is a function. If I want to know if this one's inverse will be a function, I draw a horizontal line. Notice here, if I draw a horizontal line, how many times does it cut?
Twice.
Twice. Is this graph a function? Yes, this graph is a function because a vertical line cuts once. Is this graph a function? Yes, because a vertical line cuts once. Is the inverse of this guy a function? No, because a horizontal line cuts twice. Do you get what I'm saying?
Wait, sir. You see, if you remove the first one,
Yeah.
it's only gonna cut once.
Once. So in other words, this graph, f of x,
Yes.
if a vertical line cuts him once, does it make this one a function? That's the test. Yes. If I only cut once, then I'm a function. But if I turn him around, a vertical line will cut him 2 times. So the inverse is not a function. But let's say I haven't turned it around. I'm still looking at the original one, and I want to know if I take the original one and I turn it around, will the inverse be a function? So what I do is I take the original one and I draw a horizontal line, because if I turn it around, that horizontal will become a vertical. Do you understand what I'm saying? So if a horizontal line cuts me twice, I might still be a function. Like here, a horizontal line cuts me twice. But even the inverse of this thing will still not be a function. And so the inverse of this one isn't a function, and the original one isn't a function either. But in a parabola, the original one is a function because a vertical line cuts it once. But the inverse is not a function because a horizontal line cuts it twice. So I must decide, okay, I'm only going to look at x values, like these x values, so that a horizontal line, I'm going to ignore all the places where it will cut twice. And then I'll have to start here. So I'll have to start here, and from here onwards, either left or right, you can choose. So I'm either going to take x is bigger or equal to 0, or x is smaller or equal to 0. Okay. Notice that for a parabola, this is not always the case. It's not always x is bigger than 0 or x is smaller than 0. It depends where the turning point is. It's a turning point that makes it go. So no matter where this turning point is, I'm going to take either the left side or the right side from this value here, x value here. In this case, the turning point is just at 0. Okay. So I say that because we'll get into some questions now. Okay, let's look at that one before we get into the more complex questions. Y is equal to b to the power of x. I swap x and y around. So what type of equation is that? What type of function is this? Thank you, exponential. How do I recognize an exponential function? A to the power of x squared has also got a power. The x is in the exponent. The unknown, the x value is in the exponent, then it's exponential function. Okay? So, if I swap x and y around, now I see, oh, now my y is in the exponent. How do I solve, if I had to solve y now, how do I solve an unknown in the exponent? You use logs. Okay, so in logs, we know that the exponent becomes the answer. The base stays the base, but the answer goes inside the log. Sorry guys. So now let me just give a value for b. 2 to the power of x. What would the inverse be? Y is equal to log 2x. Let's take a value like this. Y is equal to negative 4x. Okay, you don't have to go and remember, let's just swap it around. X is equal to negative 4y. Okay, can I apply logs? Is my base negative 4? No, my base is not negative 4. That gives me a negative 4 base. The negative in front of the 4 is not really the 4's negative. It's actually negative 1 times 4 to the power of y. The y and the negative are not associated. The negative is multiplying. So this is actually something like this. Negative b to the power of y. The y, only this is the base exponent. That's actually a negative 1. Okay. So in order to progress, I must first get rid of the negative. I can't apply a log until I have a base exponent all by themselves on the one side. So this becomes negative x 4y. And then same thing applies. My exponent becomes my answer. My base stays my base. And my answer goes inside there. Let's look at one more. Let's say y is equal to 2 to the power of negative x. Swap x and y around. So I got x is equal to 2 to the power of negative y. Can I use logs?
No. You have to say 2 to the power of 1 over x, then you can use logs.
2 to the power of 1 over. No, is this a base and an exponent pair?
Oh no, sorry.
Is this a base and an exponent? Yes. Is this of the form b to the power of exponent? Like, yes, then I can do. It's only when there's things outside of this, like there's a negative in front or plus 3 there or whatever, then I must get my base and exponent by themselves. I've got my base and exponent by themselves. Yes, the exponent's a little bit simplified. It is, but we can use logs. So log says my exponent becomes my answer, negative y, log, my base stays my base, 2, and my answer goes inside there. But I have to solve for y. I want to get y on its own. That's the point. So I must just divide both sides with a negative 1, or multiply with a negative, whatever. But if negative y is equal to that, then y is equal to negative that. Make sense? You guys following me? Okay, so if we go back here, we've come to some difficult ones. Now I'm not going to do this one. This one is simple enough. Okay, how about you guys do this one? Find for me the inverse of f of x, this expression. Find the inverse of that. So this one we get 1 over 5x plus 3 over 5. Okay. That looks good. Okay, let's look at that one. That one is slightly more difficult. Okay. Oh.
So didn't you write 2 over 5?
Did I? Oh, I did. Thanks. Okay. Let's write that one. They give us fx, it's probably called something else, doesn't matter. X squared minus 4x plus 4. Okay, so we're just going to replace f with a y. And then what's our first step?
X is equal to...
No? No, we're trying to find the inverse. Swap. So y squared minus 4y plus 4 is equal to x.
But can't you just say x is equal to y minus 4? Yes.
Oh, were you doing that? Sorry. I thought you were replacing x with something. Sorry, yes. Okay, next step. Just the idea. What am I supposed to do now?
Factorize.
No, you put it into y.
You want to solve y. Okay. The best way to do that is to factorize. If it was an x, we would have factorized. So we factorize and we get y minus 2 squared is equal to x. Now I still want to get y on its own. What can I do? Square root on both sides. What must I do when I square root? Plus minus. Okay, so now I get y minus 2 is equal to plus minus square root x. And now I can get y on its own plus 2 like that. It's not that difficult, you see. The process is simple. There's a few tricks just on how to get y on its own sometimes. There's not tricks that you don't know. Okay, the next question here is an important question. I already did question 2.
Oh, so I know.
So how do you do this question?
Sorry?
Yeah. There's some geometries now. Just one.
So how do we determine the restriction?
Okay. So again, give a restriction for the domain so that the inverse is a function. So if I look at this, okay, if I were to draw it, let's not draw it perfect, but let's just draw it. It's a parabola, isn't it? Do you know that this is a parabola? Okay. How do I test if an inverse will be a function? I draw it? No. I draw a horizontal line. The horizontal line doesn't tell me if this is a function. It tells me if the inverse will be a function. Okay? So this horizontal line fails. Why? Cuts 2 times. So how can I restrict the domain so that it cuts only once? Well, it's fairly simple. All I need to do is I should just look at one of the 2 legs. Either this leg okay, either this leg or that leg. Now if I restrict the domain, I'm talking about x values or y values. If I restrict the domain, x values. So I want to know what are the x values associated with this leg, or depends now on which one I choose. What are the x values associated with that? So I need the x value of what? Turning point. I want this x value. How do I find the turning point for a function? Good. Negative b over 2a. Either that or you take the derivative and make it equal to 0. That will give you the same answer. But I can just take negative b over 2a. b is negative 4, so negative b is positive 4. Divided by 2, a is just 1. So that would just be a 2 is equal to 2. That is the x value of the turning point. In other words, if I wanted to restrict the domain so that the inverse will be a function, I will only look at x values greater or equal to 2 or x values less or equal to 2. One of the 2. Okay. So if you put any one of those 2 values in here, for example, x is greater or equal to 2, that would have been correct. You get it? Not difficult, huh?
Yeah.
How's about you guys try this one again on your own? So let's look. So we have y. Let's get this out of the way. We have y is equal to, what was it? 2. Actually, let me just go here. I've got the answer here. There we go. We swap x and y around. Then we get the base exponent by itself, the 2y. So on the other side I've got x minus 4, and then I do the log. Log says my exponent becomes my answer, my base stays my base, and what used to be my answer goes inside the log. You see that? Okay. A question. What is the equation for the asymptote of the inverse? So, in order to answer that question, you don't need to know much about logs. We need to know the asymptote of the exponential function. What is the asymptote of this function? You mean what is an asymptote?
So they have the answers.
What is your answer?
It's just secretly whispering to you.
Whisper. Okay, what's the answer, Paulina?
4.
4 is not an equation for an asymptote. You're right, it's got something to do with the 4, but an asymptote is an equation. It's something equal to 4. Y equal to 4. Okay, so let me draw you that graph slightly. So this graph looks like this. Okay, the original one looks like this. So let me draw for you this. Was it a 2? Yes. Okay, so if it was just y is equal to 2x, if it was just y is equal to 2 to the power of x, the graph would look like this. Okay, and the point being is that y is equal to 0 would be an asymptote, because this expression, no matter what value I put in for x, I'll never get 0. X can be any value, and I'll never be able to get to 0. Also, because there's not a negative in front, this thing can never be negative. So this graph can never cross the y equal to 0 line. Now I say plus 4. So what do I do with the graph when I add plus 4 at the end? What does it do to every y value? Every y value gets 4 extra. So what used to be there, this is when x is 0. When x is 0, y, this will be 1. So this is the point 1. But now I say plus 4. So 3, 2, go. Now it used to be that y equal to 0 is the line I cannot reach. What will be the line I cannot reach now? Plus 4. So this is what this graph will look like. The same shape, but 4 shifted up. The asymptote used to be y is equal to 0 for any base exponent alone. That's the asymptote. So that I like to use the general expression. You know mx plus c is general for, or ax plus b, general for straight line. I like to use for exponential expression y is equal to c times bx plus a. And then the a I call the asymptote. And it must be y is equal to a because it's a horizontal line. Horizontal lines have an equation y is equal. So this one's y is equal to 4. That is for f of x. Or in this case I think it was h. That's for h. What would be the asymptote for the inverse? No, what is the inverse compared? How do we get the inverse? By doing what?
Interchanging
X and y. So if the original one had an asymptote at y is equal to 4, the inverse will have an asymptote at x is equal to 4. Get it? It's that simple. So in other words, if I had to draw this inverse, I will just swap all of the x and y's. So where I used to have an asymptote at y is equal to 4, I will now have an asymptote at x is equal to 4. Okay, if I used to cut there at 5, okay, because it's 0. 2 to the power of 0 is 1. 1 plus 4 is 5. So now I will cut at x equal to 5. I used to have my flat side, let's call it the flat side, on the negative side of x. Now I'll have my flat side on negative side of y, which is the bottom one. So this one will look like this. That is the function y is equal to log 2x minus 4. You'll notice that one y is equal to log, if the normal log function looks like this. That is just y is equal to log 2x. Now notice what happened to the x. I subtracted 4 from it. What happens when I subtract from my x values? My graph shift to the right. It's very odd. But when I add to my x values, my graph will shift to the left. When I subtract from my x values, my graph will shift to the right. There's a reason for that. You can go and look at the video I made with the other class. I explain it in there. Okay. That video is online, guys. It is after the mid-year exam. There's a page with video memos, but you have to unlock that module. So if you haven't finished term 2's work, it's no use. Okay guys, I don't want to go into this, but I just want to show you how simple this was. This was now the most complicated part of this one. It just gives us an equation here. I don't want to go through everything. Tells us, this is true, by the way. This is a formula that gives us the radius or the distance that the Earth is away from the Sun, and then v is the velocity that the Earth is traveling at when the Earth is that distance away from the Sun. So this gives the distance that the Earth is away from the Sun, and we know, and then we can calculate the velocity. So the first question asks us to show that the equation for the velocity of the Earth in terms of the distance that it is away from the Sun in r can be given by that. There's the formula that we have velocity. We want to have velocity as the subject of the formula. So all I do in here is solve for v. If you get v by itself, you'll get that. So how to get v by itself, now that's going to be your problem. I'm not going to go through that. Okay, but it's simple. It's an equation with a denominator. What do I do when I have an equation with a denominator? Multiply with the denominator both sides, and then you just continue to get v on its own. Okay, and you see v has a square. How do we, in the end, we're going to solve. You'll actually see here, I've got the answer down here. All I do is I multiply both sides. This looks weird. Okay, I divide it with the, what is going on here? Yes, I multiplied with the 2 mu on this side, and this seems to have been just a little bit different. Oh, and then I just flipped the 2 around. I flipped the 2 around. This fraction a over that one over that. I don't know why I did it like that. I don't like that. Okay, and then I divided, after it's been flipped around, I divided av squared with a to get v squared, plus mu divided by a, because remember I've now flipped it around. I just didn't have that step there. Okay, I just want to show you what I gave marks for. The first mark went for just getting v on its own, v squared on its own. The next mark goes for taking the square root on both sides, because once I get v squared on its own, I take square root on both sides. And now, why didn't I have a negative in there? Because when I take the square root, it should be plus minus. Now, those of you that have physics will understand that, well, we get positive and negative velocities. Positive, it's approaching; negative, if it's going away. So a plus minus would have made sense, but since in this case we're only considering really his speed, how fast he's traveling, negative doesn't necessarily make sense. Okay, and then anyway, the Earth is only going in one direction around the Sun, so negative doesn't make sense anyways. Okay, on this one, the next question was very simple. It just asked, determine the velocity that the Earth is orbiting when it's this far away from the Sun. So all we would have used is this formula and just replaced the radius with that value and then find for V. And then the next question is, the Earth can be anywhere between, and it gives a distance here and a distance there. That's the limits for the radius. The Earth, this is the closest it can be to the Sun, and that's the furthest it can be from the Sun. What is the minimum velocity that it will have? So they gave us the minimum radius and the maximum radius. Now most people just took the minimum radius and substituted it in there. But notice here, if velocity increases, the denominator increases. If the denominator increases, the fraction decreases. Do you understand what I'm saying? If I make the denominator 1 over 2 is bigger than 1 over 4, isn't that true? You guys get what I'm saying?
Yes.
Do you get it, Takuta? Would you agree that 1 over 2 is bigger than 1 over 4? So if I increase the denominator, the fraction itself decreases. Make sense? Okay. So in this equation, if velocity is bigger, radius is smaller. Which means a smaller radius will give me a higher velocity. A higher radius will give me a lower velocity. So guys, here's the trick before you do any question in an exam. Think. That's it. Don't just do what comes to your mind immediately. Just think. Okay? Does the minimum here mean a minimum in velocity? Well, just go and look at your formula. Just think a little bit. And these are why these values are called problem-solving questions. It requires you to think. Now, there's only 10% of that in an exam, which is very sad. 15 actually. The rest you can just do by just doing. But anyway, you can see this is, for example, problem-solving value. Okay, great. Let's stop this here, and then I'll just do the memo for the control test as well. There was an inverse question in the control test.